Hey there guys, welcome to Unit 7. Unit 7 is all about gas laws. In Notes A, we're going to look at kinetic molecular theory, specifically how it applies to the behavior of gases. Then we're going to look at three main gas laws. Our first three will be Boyle's Law, Charles' Law, and Gay-Lussac's Law. So first, gases do some typical things. First of all, a gas is a phase of matter, and so it will have mass and take up space. Gases are also known for exerting pressure. So we're going to talk very specifically about where that pressure comes from. The other cool thing about gases is that they have compressibility, meaning the spacing between the particles can change. So they're going to be able to expand or compress in order to fill different size containers. So these are some cool things that gases can do, and it all has to do with their kinetic molecular theory, or the theory that explains how those gas particles move. So before we get into the specific inferences for gases, let's recap real quick what our three main postulates for KMT were. The first postulate said that all matter behaves like particles. And this is better than wave motion for us, right? So we have our particle motion. And then the second postulate says that if I increase the temperature of a gas, that means they're going to have more kinetic energy and therefore move faster. And that was a really important one that we focused on with the phase changes, showing that the particles would move faster, and that's going to cause them to have different spacing and therefore be either solid, liquid, or gas. And then our third postulate is actually going to come back up a lot in this unit. If I increase the mass of a substance, then that's actually going to decrease its motion, making it slower. So we saw that increased temperature would increase the motion, whereas an increased mass would decrease the motion. So we're going to look at these postulates specifically as they apply for gases. First of all, focusing on the one that we started with back in Unit 1, if I increase the temperature, I increase the kinetic energy. So that would make gases the most energetic substance existing at the highest temperatures. Those crazy fast particles are going to be very, very far apart, leading to the particles being mostly empty space. And then they're also going to be very, very small and separate. So most of the volume would be not particles. Like in this box, the white space would be more of the volume than the red space. So they're very far separate little particles, leaving mostly empty space in between. Something else about the particle motion that we didn't get into much last time was the type of motion. So they actually do move a lot, and although that seems very chaotic, they move in straight lines. So if I have a particle of gas, it's going to continue to move, kind of following the law of inertia, in a straight line until it hits something like the wall of the container. Once it does that, it would bounce then or be refracted somehow, but continue to move in a straight line. Say I have multiple particles moving around. If those two particles hit each other, they're going to bounce back from each other with the same energy that they put into the collision, they're going to get out of the collision. So we call that an elastic collision, kind of like how an elastic band would snap back to the way that it started. And elastic collisions means both particles leave with the same amount of energy that they came in with. They may exchange energy. I give you $5, you give me $5, we both have $5, big deal. So there's no net change for them. They interact, but they leave the interaction with the same amount of energy that they came in with. And this is unique to particles colliding inside, gas particles colliding with each other. Okay? This is not true with the collision with the wall of the container over here. As a matter of fact, that's where pressure comes from. Pressure is exhibited as particles hit the wall of the container. The wall of the container is stationary. And so the energy transfer would be from something with energy to something that's stationary. And so you're going to get a difference. You're going to get something called pressure, only with the walls of the container, not from the collisions within the particles. So let me erase this a bit. 1 second. So that actually is the second sentence here. The gas pressure is caused by collisions with the walls of the container. So one last thing that I want to mention about gas particles, though, is that their motion is defined by something called the Kelvin scale, absolute energy. And so every conversion or every calculation that we do in a gas laws unit is going to need to be in the Kelvin scale, because we always want this temperature to be the absolute temperature. You may have heard of absolute zero, where there is absolutely zero particle motion. That's the scale we want to be on here, so we're always going to want to convert to the Kelvin scale. So that should give you our inferences from kinetic molecular theory as they apply specifically to gases. All right, let's talk a little bit about the types of problems we're going to work here so we can go over some of the basic variables that we're going to use. Yes, they're going to be a lot of word problems. These are more of an algebraic type of word problem. So first thing I want to talk about is the difference between a variable and a unit. Let's talk about a formula we've used already. Density equals mass over volume. So we should be pretty familiar with mass. We've been using it in our conversions, right? What's the unit for mass? It's not m, it's grams. So we could say the mass of something is 34 grams. So then we would be plugging in 34 grams for the letter m in the formula. So you want to make sure that you're not confusing variables and units here. We're going to have some very complicated units. So you want to make sure the units are what's coming after the number that are part of the measurement, whereas the variable is what the formula is giving you, where to plug things in. You're also going to have lots of different units, so we want to make sure that we remember if the units don't cancel, you might need to use something called dimensional analysis. That was back where we were converting, for example, milliliter to liter, in order to make the units be able to cancel. The other piece of advice I want to give you up front is not to use x. Yes, it works the same, but if the variable is p, keep it as p. That's going to help you be able to make sure that it actually means pressure and you're getting units for pressure. So don't use x, but it is still kind of going to be a lot of solving for x. All right, so let's talk about the specific variables that we're going to be working with gas laws. The first, V, would stand for volume, or the amount of space something takes up. Volume is typically measured in liters, although you may also see it in milliliters or centimeters. By the way, you should also know that a milliliter and a centimeter are actually equal to each other. 1 milliliter is equal to 1 cubic centimeter or 1 cc. Next, we might have the letter N. Remember N in like the hydrate number? CuSO4 attached to some amount of water. Some amount of water relative to our hydrate. N is the variable for moles, or the generic amount of substance. One problem that's going to come up sometimes is, although we need to plug moles into the formula, they may give you grams. But fortunately, we are pretty much pros by now at converting grams to moles using our molar mass. Next, we have T for temperature. So temperature, the thing is, it has to be in Kelvin. So sometimes they might give you Celsius, and you're going to have to add 273, or more precisely 273.15, in order to convert to Kelvin. P would be our pressure variable, and this is probably a newer variable. You may not have seen very many units for that. The standard unit that we have seen here and there is ATM for atmospheres. Another one that throws everyone off is millimeters of mercury, MM space Hg, meaning the symbol, chemical symbol for mercury. So this actually comes from the idea of those mercury thermometers, where you can see how high they're rising and how the pressure is an effect on that. The millimeters of mercury. T is short for someone's name, and then K, PA. PA would be pascals, again a name, and then kilopascals is just going to get rid of the scientific notation on that. We'll look at these conversion factors in just a minute. But let's focus on what pressure is for a minute. Pressure is basically a ratio of how much force is applied over a given area. Keep in mind, let me draw a little fake balloon here, that the particle colliding with the wall of the container would be the only source of pressure. Particle colliding with other particle does not contribute to the pressure. It's only the pressure, only the collisions with the wall, so the only area I am concerned with would be the actual area of the balloon. What is it actually hitting? So kind of like, what's our surface area? And we want to look at what the force is on that surface area. So a couple examples. Why does wearing high heels hurt? You've got your whole body pushing down on your feet, and it's all coming to a point on this very small area. So if you are putting force on a small area, force being big, area being small, just think mathematically even, large number divided by small number, you're going to get a big answer. So you get a large amount of pressure if you're applying force over a very small area. On the flip side, we can also spread out the force over an area to decrease the pressure. Here we've still got a nice amount of force going in. This guy is sledgehammering on a bed of nails. So these are all individual nails kind of trying to sandwich this guy. But the thing is, because those nails are so close and so spread out over such a big board, the actual surface area is pretty big. So because that force is applied over a very large area, dividing by a small number would produce a smaller answer. So there's not enough pressure actually being applied in any one given spot in order to puncture the skin. That'd be different than just stepping on one nail. If you stepped on a bed of nails, the idea is it wouldn't be enough pressure because it's spread out over a larger area. Wouldn't recommend trying it. That's the theory. All right, so I mentioned we'd look at some conversions. Here, everything is set to compare to 1 atmosphere, which is our normal pressure. So it would be equal to 760 millimeters of mercury or torr, which would essentially mean that 1 millimeter of mercury is equal to 1 torr. You also can see here the regular pascals and why they would convert it to kilopascals, so we don't have to deal with the scientific notation. And then barometric pressure versus atmospheric pressure is pretty much a 1-to-1. So these are some different conversion factors you can use if you don't have units that match up in a problem. Last thing I want to mention about some different variables is remember our good friend STP? When we had 22.4 liters was equal to 1 mole at STP. STP was always set at 273 Kelvin or 0 degrees Celsius and 1 atm. This also can be called normal pressure. There's no such thing as normal temperature, but normal pressure is 1 atm, standard pressure is 1 atm, and standard temperature is 273 Kelvin in gas laws. There is a different value for thermodynamics, but for our gas laws, we have standard temperature and pressure being 273 Kelvin and 1 atm. The catch with the word problems is sometimes they will not actually tell you these numbers. They will simply say, we are at STP or at standard pressure. They will say either the words or the letters, and you have to know those things mean these numbers, and then be able to use these numbers to plug into formulas. So keep an eye out. Don't let it throw you off. If it seems like you don't have enough numbers, look for the STP and see, can I add in these known numbers? All right, so that kind of wraps up all of our different theories behind gas laws and the different variables to watch out for. All right, so let's dig into Boyle's law. So Boyle's law is the relationship between pressure and volume. These two things are related in an inverse way. What that means is if you increase the pressure, you would decrease the volume. And on the flip side, if you decrease the pressure, you would increase the volume. Whatever one does, the other does the opposite. So if I applied pressure to this balloon, the balloon should be trying to get into a smaller volume. Because it's sealed, it tends to pop. That's Boyle's law in action there. The increased pressure is trying to create a smaller volume. So the idea here is that there's an inverse relationship as long as the temperature and the amount of gas, or the number of moles, are constant. So we can establish a relationship between two variables at a time during our first 3 gas laws. We have a shorthand for this. Not that it's super important at the moment, but the more advanced chemistry you take, the more advanced science in general you take, the more you'll appreciate shorthands. So this just means proportional to. So volume is proportional to pressure is not really true because we can see that they're inversely related. So we would say it's proportional to the inverse. And if you put something in the denominator, it's the inverse, like inverse seconds. So volume is proportional to the inverse of pressure is how this would read. This gives us a slightly different formula than your typical proportion. We would read this as P1 V1 equals P2 V2, or V1 P1 equals V2 P2, either way. So when we solve word problems, the idea here is that we're going to be given 3 of these variables and solve for the fourth. I tend to think of this as initial and final. What are my initial pressure and volumes? And then I make a change, and then what does it change to in the end? So let's look at one of those word problems. The first thing I like to do to a word problem is to isolate the variables. Word problems tend to intimidate people, so I try to make them not word problems to start with before I start trying to undertake the algebra. So let's look at this one. A sample of gas occupies 12 liters under a pressure of 1.2 atm. What would the volume be? So whenever you come across what, it's an indicator of what the unknown variable is. And then what about if the pressure were increased to 3.6 atm? So what I've got underlined right now are my variables. I just need to identify which one's which. So the first number was the 12 liters. The units can help indicate what the variable should be. So liters would indicate volume. Next I have 1.2 atm. And atmospheres was a unit for our pressure. What indicates the unknown, so the volume is going to be a big old question mark. And then we've got 3.6 atm, and again, atm measures pressure. So notice that we have some repetitious variables here. We want to make sure that we isolate which ones go together, which ones are the initial ones, which one are the final ones. So it says we've got the 12 liters under the pressure of 1.2 atm. So those two go together, and my unknown is at the 3.6 atm. So those two go together. So you can use subscripts to do your pairing. So these are my two sets. Initially, I have this volume and pressure, and then later, the volume would be what if I adjusted the pressure. The first thing I would do to solve is write down the formula. You're gonna have to choose your formula and show that you're using the right one. This is actually a really big deal in like your AP tests. They wanna make sure that you're using the correct formula. So just to make sure the grader is giving you the points that you wanna write it down. Before I start plugging things in, I want to check my units because I know that I'd have to have the same unit for them to cancel out. So if these were not matching, I would want to change one of them. Say if this were in millimeters of mercury and this were in atm. It doesn't matter which one you change, but you need them to match. Liters then, of course, would then give me liters for my unknown, which unless it specifies otherwise is fine. Now let's start plugging things in. So P1 is going to be 1.2 atm. And yes, it's very important that you plug your numbers in with those units. V1 is 12 liters. P2 is the 3.6 atm. And then V2 is my unknown. Notice how I didn't use X. I'm using V2. We want to stop using X and start using the actual variable that we're trying to solve for, in this case, the second volume. We're still going to treat it like X though. So how am I going to isolate my variable? I'm going to divide both sides by 3.6 atm. So that's going to allow me to then isolate V2 on the right. That was the whole point, right? And now I can reduce this part. The first thing I would do is look at my units. I have an atm on top and an atm on the bottom, and those will cancel out, leaving me with liters. Before I even bother touching the calculator, I want to make sure that the units actually make sense for the variable that I'm solving for. Does liters measure volume? Yes. So that's a good indication that I have this set up correctly. So now I can go ahead and solve the math. What is 1.2 times 12 divided by 3.6? And that will actually give me my answer for volume on this one. So that would be 4 liters. Why the 4.0? Why not just 4 liters? Well, when we're multiplying and dividing, which is going to be what we're doing in our gas laws, at least for most of them, we're going to be going by the least number of significant figures. All of these have 2 significant figures, and so I want to make sure my answer has 2 significant figures, so we've got the 4.0. All right, let's look at our next gas law. For Charles's law, we're going to look at the relationship between temperature and volume. So Mr. Peep over here goes in the microwave, and so his particles start to vibrate more quickly, so they have more kinetic energy. And if you remember, that's your definition for temperature, so that the particles have a higher average kinetic energy. So as those particles are moving faster, the volume would then get bigger. So Mr. Peep expands and eventually explodes. So the gas inside the marshmallow is getting bigger, taking up more space. As far as the math problems go, you want to be just very careful when it comes to temperature that you are only using the Kelvin temperature. The Kelvin scale is specifically designed to measure the particle motion, and that's what we're really trying to capture here when we're looking at the particles of gases. So we're looking at the relationship between temperature and volume, which means the other 2 things that have to be constant are your pressure and your moles, the amount of gas. So as long as those things are constant, we can look at just the relationship between these 2 variables, which would be a direct relationship, which means the shorthand gets a little easier too. Volume is proportional to temperature. And even better, the math is going to look just like a normal proportion, where you have similar variables on top and bottom. your initial on one side, your final on the other side. And of course, you could flip this any which way. The idea here is you've just got a simple proportion out of volume and temperature. So let's look at a word problem with Charles's law. I'm going to approach all word problems in this unit the same way. Find my variables first, write down the formula, plug and play. So first we've got 117 milliliters. That is at 100 degrees Celsius. So over here, notice the decimal there too. That's going to make it 3 significant figures. Then I've got 234 milliliters. And then I'm looking for, where's the word what? What temperature. So now I found my 4 variables. So I want to make a list of them. 117 milliliters. Milliliters is going to measure volume. Then I've got 100 degrees Celsius with a decimal, degrees Celsius, and degrees Celsius would measure temperature. And then what temperature means I have a T question mark. And then the 234 milliliters will give me volume. So does the 117 go with the 100? Yes, it says 117 at 100. You don't want to assume that just because they're in order that the first two go together. You do want to go back and check the wording on the question because they can kind of try to trick you. But this one does say that the 117 is at 100 degrees, and then we're looking for the temperature at the 234 milliliters. So those are my 2 sets of initial and final. Because I'm looking at temperature, anytime I'm in gas laws, I want to convert the temperature to Kelvin. So you want to get in the habit of doing that automatically. So what is 100 plus 273? 373 Kelvin. Let's talk sig figs on temperature real quick. When you add 100 to 273, you are now going by the least number of decimal places, which would be the ones place. This can take a temperature like 25 degrees Celsius when you add 273 to get 298 and turn a 2 sig fig temperature into a 3 sig fig temperature. So you want to be really careful with your temperatures because typically they're going to have 3 sig figs because you're adding 273. And then we would consider them to have 3 significant figures as you go and you plug them into the multiplication. All right, let's go ahead forward with this question. We're going to write down our formula first. V1 over T1 equals V2 over T2, or vice versa, either way. So on top, I'm going to plug in my 117 milliliters. On the bottom, I'm going to plug in my T1, not in degrees Celsius, but in Kelvin. 373 Kelvin. And then for V2, I've got my 234 milliliters. And I forgot to point out, by the way, make sure they're in the same unit, otherwise you'd have to convert. Now we're looking for T2. So this looks like a proportion. And how do we solve those? We're going to cross multiply. So let's go this way first. I've got 117 milliliters times T2. And then this way, I've got my 373 Kelvin times the 234 milliliters. So I'm trying to isolate T2. Now this kind of algebraically looks similar to the last question. To isolate this, I'm going to divide both sides by the 117. So that, of course, will isolate T2 on the left. And now let's look at units first on this side. My Kelvin doesn't have anything to cancel with, but my milliliters does. If both milliliters cancel, the unit left would be Kelvin. Does Kelvin give me a temperature? You want to make sure that that makes sense before you bother with the calculator. Since that makes sense, let's go ahead and calculate. What is 373 times 234 divided by 117? What is our Kelvin temperature? So we should get 746 Kelvin. This question happened to ask, go ahead and express it in Kelvin. If they are kind of tricky up here and they ask for degrees Celsius, you still have to work the problem in Kelvin. And then once you got to this point, you could simply subtract 273 to get the answer in degrees Celsius. But you will get the wrong answer, particularly if it's a negative degrees Celsius here, if you work the problem in Celsius. All right, on to our very last gas law, Gay-Lussac's law. So our last two variables to talk about are pressure and temperature. So you may be familiar with a hot air balloon. At the base of the hot air balloon, there is a little flame there, and that's how the hot air balloon is able to kind of stay in the air. So how does that work? Well, the flame is increasing the temperature of the gas. It is heating up those gas particles, and according to the second postulate of kinetic molecular theory, that means that those particles will then move faster. So those faster particles are going to be hitting the walls of the container, or the balloon sides, much more often, and that will then create more pressure. So as I increase the temperature, I'm going to increase the pressure. This direct relationship, you just got to be careful to show in Kelvin mathematically, because Kelvin is what defines your absolute particle motion. When you're looking at this relationship alone, you want to make sure that volume and the number of moles are constant. This direct relationship can also be shown with shorthand. Pressure is proportional to temperature, and then the math is also going to be just your typical proportion, where you have like variables on top versus bottom, and initial versus final on either side. So Gay-Lussac's law, direct proportion between pressure and temperature. Let's look at one last word problem here. So I'm going to approach this word problem the same as before, where I go through each variable and isolate it. So I see a number here, 20-liter cylinder, contains 6 atmospheres at 27 degrees Celsius. I see the word what, so I can find out that pressure is my unknown. And then the next number I come to is that we're heating the gas to 77 degrees Celsius. So focusing on the numbers and the units. So if I make my list, the very first number I could write down would be this 20 liters. And liters would measure volume. The next number that I come to is the 6 atmospheres, and atmospheres measures pressure. Then I see at the end there the 27 degrees Celsius, and degrees Celsius measures temperature. Now I'm at my unknown, so my pressure is the big question mark here. And then the last number to put down is the temperature of 77 degrees Celsius. This problem's a little different than the last two because I have like an extra variable. Normally we only had 4. The formula only has 4, but we have 5 given in the question. So we've kind of got to play the game, which one of these does not belong? Like, which one do we not need right now? And to think about that, you've really got to figure out what's not changing. Well, the pressure changed. I don't know what it changed to. That's kind of the whole point of this problem. But I do know that I'm going to need pressure in my formula. And the temperature changed as well. So I know I'm going to be looking at a change in temperature and how that affects pressure. So that sounds a whole lot like Gay-Lussac's law, right? It never says that the volume changes. So why would we just assume that it changes? We actually will look at a law later where all 3 variables can change, but that isn't what's presented here. So we're going to focus on just how this temperature change affects the pressure change, which is Gay-Lussac's law. So I'm going to write that down. P1 over T1 equals P2 over T2. All right, before I can jump into plugging stuff in, I've got to check my units, and temperature is always got to be checked because it always has to be in Kelvin. So I'm going to add 273 to each one. Remember, when we do that, it's going to change my 2 sig figs into 3 sig figs because we would be going at the ones place. So 27 plus 273 is 300 Kelvin. And I'm going to put a decimal at the end of the 300 to indicate that that has 3 significant figures. Then 77 plus 273, I cannot do in my head. 273 plus 77 is 350. So again, we're ending with a 0. So I'm going to put the decimal at the end to show that it has 3 significant figures. Now I want to plug these numbers in. So which ones were the first set? We've got to look at what goes together. 6 ATM was at the 27 degrees Celsius. So we happen to still be in order this time, where P1, T1 are my 6 and my 300, and the unknown is with the 350. So I'm going to plug in the 6 atm on top first, and then my 300, the temperature in Kelvin for T1 with the decimal. Then I have my unknown of P2, so I'm just going to write P2, and then my temperature in Kelvin was 350. So now I have my proportion. It's time to cross multiply. So first I've got P2 times 300K. And then going this direction, I have the 6 atm times the 350K. Now I'm going to isolate P2, which means dividing both sides by the 300K, which will isolate P2 on the left. And then the first thing I'm going to do on the right is look at my units. The atm has nothing to cancel with, but our kelvins cancel. So that means atm will be the unit for my final answer. Is that a normal unit for pressure? Yes, it is. So that tells me that I've got this set up correctly. So now I'm going to actually do the multiplication, 6 times 350 divided by 300 to get my number. But I want to point out something different. This time they have different significant figures. 6 atm only has 1 sig fig, whereas our temperatures both have 3 sig figs. So how many sig figs should our final answer have? Well, if we're going by least number of sig figs, it should only have 1. So what is my pressure in atm to 1 significant figure? Should be 7 atm. There we go. Final pressure, 7 atmospheres. Being careful about significant figures and unit conversions. All right, guys, that's your first taste of gas laws, the main 3, looking at only 2 variables changing at a time. In Unit 7, Notes B, we're going to look at some more gas laws where we look at equations where more than 1 variable can change at a time. See you there.